Thank you. As they transfer over my slides, I'd like to give a shout out to Dr. Mohammed Sabori, who was really the brain power behind this research work. I kind of steered him in a direction, and then he took it from there. I think that he certainly would be remiss to miss this, but he's in his home country teaching some college classes right now, so kind of filling in for him on this presentation. I'd also like to talk about some of the folks that did participate in this research as well. And the research is optimizing cold-in-place recycling, and we're using CIR because we wanted to do this research in a more of a limited environment where you're using 100% wrap to reduce the variability. Looking at applications through fracture energy performance. The funding for this came from the Minnesota Local Road Research Board, LRRB. They have been really the champions in advancing cold-in-place or in-place recycling in Minnesota for a number of years. The counties have done an awful lot in making sure that everything is moving forward. You heard Joe Triplett earlier this morning. He was one of the early champions that got a lot of this stuff going in terms of the development of engineered emulsions, development of different processes, advancement of equipment, and that type of thing. I also like to thank Carver County, who was the sponsor of the research, submitting it through the Local Road Research Board, and American Engineering Testing, who was another testing firm in addition to our testing firm, Braun Intertech, that worked together to make sure that we had repeatability, interlab correlations, and research that was going to be able to advance. And then last but not least, the Minnesota Department of Transportation, who also participated in the research from a testing standpoint and providing direction moving forward. So again, we're talking about cold-in-place recycling. We're talking about partial depth rehabilitation with 100% wrap. It main purpose is to retard or hopefully eliminate the reflective cracking coming back from the underlying pavement that's left behind, and has shown phenomenal performance across many agencies within the state for many decades, as it has been improved over that time frame. And this is just a quick look at the mixed design criteria, and you can see that not all the standard criteria that was developed as the original guide spec out of Koch Materials is there. The indirect tensile test was not part of it, but you can see that the raveling test and the retained stability and the dry stability is a key component. So really, to set up these designs, we wanted to look at the most commonly used stabilization materials in Minnesota, and those are engineered emulsion, high float emulsion, foamed asphalt, and cement with commodity emulsion. Braun Intertech did the designs for the engineered emulsion and the high float emulsion, and AET did the work or the design for the foamed asphalt and the cement with the commodity emulsion. As you can see here, they were all three-point designs, and the optimum binder content was determined with that three-point design, and is shown here on the right. 2.8 for engineered emulsion, 2.0 for high float emulsion, 2.2 for foamed asphalt, and 2.3% emulsion and 1.5% cement with the cement plus emulsion design. So the whole purpose here was to take the designs of these different stabilization materials in the CIR environment and then look at fracture energy as a potential improvement in the performance testing, not just for relation to crack resistance, but also wanted to look at fracture energy as a viable test to advance into the quality control, quality assurance environment. And I think Brian's going to talk more about that when I'm done, and I think that is certainly a key progression to going forward with these different recycling in place strategies and rehabilitation focuses. So what you see up here is we've got a beam, we've got a SCB and a DCT. I remember back in the old days when I'd visit with Todd Thomas about in-place recycling. And we talked an awful lot about how the big emphasis was on stiffness, strength, structural coefficients. But that missing other end of the pendulum was the flexibility and fatigue resistance. And so a lot of times we talked about how beam fatigue would be a good test to do that, but it really wasn't practical to implement. So here we've got a test that I think is going to fill that gap and not only provide a good, better performance test as it relates to crack resistance, it's also going to give us a little bit of information and indication of fatigue resistance as well. So looking at these, we came up with the SEB as the test of choice. Looked at some research work that had been done already in Illinois and also by Stéphane Charmeau in China. It looked like a test that could provide us with the information that we want and also be practical as far as carrying things forward. So you can see here that in terms of the sample preparation, you either have a gyratory specimen, or if you're talking about a field specimen, you're taking a core from the field. From that specimen, you can come up with 2 DCT specimens or 4 SCB specimens. So as you advance to doing quality control, quality assurance in the field, the ability to get more samples from the specimens is certainly an advantage when you're looking at correlating the material that's being placed back to the mix design or back to what you're trying to achieve. So we did some modifications to the SCB test machine, mainly to reduce friction, aluminum plate, and Teflon strip were part of that. As you can see, the standard normal testing mode on SCB is compression as compared to DCT where it's tension. Beam fatigue is also compression, but tried to run the standard procedure that people were using for SCB, and what we found is, looking at that load as it relates to the actuator displacement control, we didn't get any beyond post-peak behavior. When you look at a standard, you typically have a peak value here, and then you get a tail where it runs down, and the area underneath that graph that remains would be the actual fracture energy, or the integral of that line. So what Dr. Sabori came up with was looking at it from a crack mouth opening control rather than an actuator control, and through a number of repetition processes in this research, got a pretty good tail that came out from that. And so when we went back and looked at a lot of the research, we found that a lot of people were having difficulty carrying out the fracture energy test to get the full tail of the sample. And so using the CMOD control, we were able to get that, but in reviewing with different folks in the industry and academia, even though your units are joules per meter squared or a fracture energy value, it wasn't really following the accepted standard protocol, so we decided to call this value fracture index value for energy, or 5 test. And the whole point there being that we wanted to have a practical test that was going to be able to differentiate between materials that are used in the process and also be able to properly measure crack resistance and provide a test result that's certainly going to be reproducible and reliable in the field. So through a number of test verification steps, 6 engineered emulsion samples, 7 high float, 8 CSS1 samples, we were able to look at statistically using the t-test that the HFMS2S and the E are statistically the same in the results. So the DCT testing results also showed very good correlation. One thing that we did find, though, is that the high float samples were difficult to produce the specimens and maintain their integrity through the test, just because it's not a very, integrity, the test itself, or the test specimen itself, didn't have a lot of integrity to it. And that kind of related back to field performance in terms of the high float emulsions often showed rutting in the field just because they were really flexible, really soft materials, again, using solvents in the process of making the binder. So those were much more difficult to use in the testing environment, and the feedback from the DOT was negative in terms of their feeling about high float emulsions going forward. So the focus was then more on the other binders, and we looked at the SCB versus the DCT. You look at the different modes of testing, where there's tension and compression, and you want to be able to make sure that the values that you're getting from those test results are going to translate into actual performance of that material in the field. One of the things that we also did was a round-robin test between the two labs. That would be Braun Intertech and American Engineering, which we then took the samples that were produced in the mixed design phase, did an awful large number of sample set, 96 samples total, to look at round-robin and interlab correlations. You might ask, why am I spending so much time on the aspects of this test? But it's really important because, the results, especially when you start translating from mixed design to quality control, quality assurance, are very important to carry any type of rehabilitation process forward in order to have reliability in distinguishing different types of not only binding materials, but the process itself in terms of providing the agencies with the results that they want. So you can see here, Lab A results had engineering emulsion, CSS1 with cement, the high float, and the foam. All had fracture energy values for the most part between that 200 and 300 area, where Lab B results, the only thing that was below the 200 value was the CSS1 with cement. And looking at the results and coming up with a statistical analysis on them, Dr. Sabori, looked at that in depth and found that there was not a significant difference in the statistical value, looking at the p-value in his statistical analysis of the populations. So putting all that information together and looking at developing a performance specification and looking at developing some type of criteria for the 5 tests for the fracture energy value, coming up somewhere between that 200 and 250 value seemed to make sense. So one of the conclusions would be that the fracture index value for energy of the 5 test is a fracture energy test that is viable to optimize the cold-in-place recycling process, to be able to look at those materials and distinguish between them. It also showed great potential to be used as a performance specification using the SCB, which is the most practical test that could then be translated into quality control, quality assurance. Among the 98 SCB testing specimens performed in this study, only 2 of the samples failed during the testing itself. This is a success rate of 98%, which makes that 5 test even more reliable. And the statistical analysis suggested that the data sets are statistically the same for all the 4 study mixtures. So fracture energy certainly is showing that it's a viable alternative to not only look at crack resistance, but it's also potentially going to provide a means to advance into the quality control, quality assurance, which I think Brian's going to talk about further. Field performance is required to validate the laboratory testing. I mentioned a little bit about some of the field performance with the high floats or the very soft binding materials. And also looking at the curing. Some of these materials, when you add cement, you're certainly going to affect the curing because that cement's going to tie up some of the water. The emulsions, engineered emulsions, are formulated to help drive out the water. The environmental conditions, need to be addressed. So there's a lot of different variables that come into play in terms of establishing a curing or a time window to look at these in relation to each other. But the whole idea is that this is a great starting point. I think fracture energy is a great opportunity for us to be looking at the performance of these materials and getting a lot more information. And the reason that's very important, you'll be going out to the Monroe facility today. I encourage you, hopefully you'll be able to go on the Monroe mainline test section cells 2, 3, and 4, and those are recycled in place using the SFDR process, stabilized full depth reclamation. But the whole concept here is tying to performance. And when you go out there, you'll see on those sections where on I-94 Interstate Highway, they only had 3 inches, a little less than 3 inches, in fact, of hot mix overlay on top of the stabilized sections. And you think about that pavement section for an interstate highway, it seems pretty thin. But the whole concept there is kind of tying in from the previous speaker, one of the Andrews, is that the maximum tensile stresses are going to be driven down to the bottom of the bound layer. So when you are going in and stabilizing with a binder and creating a bound base, you're going to be driving your maximum tensile stresses to the bottom of that bound base. And through strain gauges out at Monroe, they found what happened was the strain then at the bottom of the hot mix layer was half of what that strain was at the bottom of the bound layer. So when you start thinking about the micro strains, that 70 to 200 value for perpetual pavement, and the fact that you're not getting the strains underneath that hot mix overlay that you would normally see if you didn't have a bound layer underneath it, that kind of shows you why that hot mix overlay is lasting much longer. And on those cells 2 through 4, they've actually doubled their design life, or getting very close to that. It's designed for about 3.5 million easels, and I think they're approaching 7 million easels on it now, and just now starting to show some signs of some cracking starting to appear. So that's some amazing performance that speaks for itself, and some of the research work that was done out there is helping us to understand why that flexible component is so crucial, so important, in addition to that strength and structural coefficient, in terms of a full equation or a full pendulum on both sides to balance both structure and flexibility or fatigue resistance in these recycle projects that we're doing. And one of the things that I've been looking at, found some research work done by the University of Arkansas, and might have been Andrew's work, not sure, but AAPT and Arizona State University. We're looking at, basically fatigue cracking origins, and what they looked at was the initiation and how that crack coalesced and propagated through material. And I think what we're seeing with this recycle in place material, it does not behave like a hot mix material. It doesn't behave like certainly a cement material or something that's more brittle. But because of the higher void value, because of the softer binders involved, the cracks, when they do form, they find a hard time, and this is kind of up on the side, but there's probably more of them, but they don't find a path to get through that material in order to propagate up through that overlay, and that's why those overlays are not seeing cracking for a much longer time than they normally would see when they're placed on top of an unbound base. So that's some very interesting research that I think is going to be carried forward as time goes on in terms of why these are performing so well, and that whole idea of how a crack initiates and propagates through different types of materials as related to different material properties like the in-place voids or the binding materials that are used in those, the flexibility and the fatigue resistance of that pavement structure. In addition, what you'll see out there was some sections that were placed this year, and somewhat because of this research, Foamed asphalt and engineered emulsion were selected for additional work on the low volume loop. And so 2 test sections were placed using cold central plant recycling, where the material was manufactured off-site and brought out to Min Road and then laid through a paver. There's 2 sections of foamed asphalt, and there's 2 sections of engineered emulsion. Each one has a surfacing of chip seal and overlay. So you've got 1 section of each on each roadway, and each of those sections use different base binders in the manufacture of the material as well. So some really interesting things to look at. I'm really happy to see some foamed asphalt get out on that roadway. One thing that I did notice that I haven't seen with foamed asphalt in the past is that very good coating on the coarse aggregate particles in the foamed asphalt section when I was out there. And you know, normally you see foamed asphalt really coats the fine aggregate, which holds those coarse aggregate pieces in place. But talking to other people in the industry, I've found that certain binders, certain asphalt cements, as related to the half-life and the expansion ratio in combination, will provide better coating in the foamed asphalt environment. And I think you know, the asphalt that was supplied here is certainly one of those, because excellent coating, probably the best I've ever seen on that material. So with that, I hopefully got us caught up a little bit. I tried to go through a little quicker because I knew you were right a little behind, and I will answer any questions that you have. Yes, sir.
What did you CIR? How do you control the durability?
Don't hold me to this, but I believe it was based on the number of gyrations that were used in the design, which probably was like 30 or 35. Right. I don't think we did. But again, that's probably getting into this whole crack initiation and propagation is probably going to be a huge factor looking forward, or going forward, especially in the quality control aspect of it. And you know, the fact that they're doing intelligent compaction now on recycled in place jobs. Not so much as measuring the in-place voids, but more making sure that a uniform applications of density are being applied across the entire roadway, which is pretty important.